get started. Lots to do today. Thank you for showing up. I was hoping that someone would be here at least, right? Looks like almost everybody. So, yeah, wife told me I had to go do that before Thanksgiving. So I got it done. All right, so here we go. A lot to do today. We're starting 8.3. We finished up last class. Wait, hold on. We're not starting 8.3. We are continuing 8.3. Yeah, we're continuing 8.3. Sorry. And the last thing we finished with was P series. All right? So now we move into this thing called the comparison test. And things start to get a little weird now, all right? So here's the whole idea. We have a series, and notice I'm not writing n equals 1 to infinity anymore, right? So we have some series, and we're trying to figure out whether or not it converges or diverges. So we look at it, and we go through Nth Term Test. We realize that it's not geometric, it's not telescopic, it's not a P series, and we're kind of just stuck there looking at it, right? And we're saying to ourselves, well, how do we do this? And we realize that the series that we are trying to figure out looks something like a series we know. All right, in some aspect, it's similar to something we're familiar with. So we actually find a series. Okay, so it's the task is on you to find this new series. So I'm using B sub n instead of A sub n. This is a different series to compare it to. And this is the key. We have to know what that series does. Like, we have to know it's convergent. We have to know it's divergent. We have to know that to start the problem. All right? And then we have two different possible cases that could happen. Let's say that the series that we have chosen is convergent. All right? So that would mean, just think about it visually, that if we were to graph this sequence right here, right? Or not the sequence, the sum, right? Well, no, let's talk about the sequence, okay? So if this thing converges, right, then what I know is when I add the terms up, right? When I add the terms up, it goes to a number, right? Yes? So if I look at this sequence, not the series, but the sequence, it's doing something, right? Whatever it's doing, right? Who cares? Then if this one converges, I have to show that A sub n is less than B sub n. So that means that this series over here, when we look at the sequence here, that these are always smaller than the blue ones. Now, what would that tell me?
That's not going to infinity.
That what's not?
The
The series, right? So look, if this series converges, that means when I take that blue one and add that blue one and that blue one and that blue one and that blue one forever, right? It goes to a number. Now, if the red ones are always smaller than my blue ones, then it can't possibly become infinite because it's always less than this one, which means that the red one, this series, must also converge. Now, we don't know what it converges to, but it converges. Does that make sense? It's kind of like we're putting like a bound on the red series and the red sequence, and then if the blue sequence converges when we add them up, then the red one has to also. Does that make sense? Kind of visually? Now let's look at this. Let's say that the one that we're comparing it to diverges. Okay, that means when I add those things up, it becomes infinite. Then it says that we have to show that the A sub n's are bigger than the B sub n's. So here's my B sub n. Again, if I go and I graph this, I've got these dots, whatever they're doing, right? But the A sub n's, if I can show that these guys are bigger than these, then my red ones are on top of them somewhere, right? Whatever. So if I add up all the blue ones and it diverges, and the red ones are bigger, then it must also diverge. Make sense? No?
It's like the opposite of.
It's the opposite of this.
Yeah,
Okay?
So you're saying if the blue one converges to a number, then the red one has to also converge to a smaller number because it's under it.
As long as it's under it. As long as this sequence stays below the blue one, if the blue one adds up to a number, then the red one's going to have to add up to a number. It can't be bigger than the sum of the blue one, right? Because it's smaller all the time.
Could it ever be where the red one would be under the blue one, but they're also diverging? Or
That's a good question. Let's do an example and you'll kind of see. Yes?
Just real quick, so they both have to just equal it to the same thing? Or like to each other, basically?
What?
For the top one? That one, yeah.
They don't have to be, they won't converge to the same number. I don't know if that's the question you're asking me.
Yeah, like let's say like the number is 4, like they both will converge.
No. So let's say we have a series we don't know what it does, right? And we compare it to a series that we know what it does. Let's say we compare it to a geometric series. Let's say we know that geometric series converges to 4. Okay, if I can show that this guy right here, these guys are always smaller than these guys, then what I can say is that this one converges. Now I can't say it's 4 though, because it can be 4, it could be 3, it could be smaller also. All I know is that it converges. And remember, what are the only two series that we actually can find the sum of? Geometric and telescopic, right? If they converge. So from here on out, it's really just convergence or divergence, right? That's all we're checking for. It either converges or it doesn't. So this is enough for me to show that it will converge without knowing what it goes to. Does that make sense? This is the opposite of that. This is saying, hey, look, if the series here, let's say this was a series, I didn't know what it was doing, but this was, let's say I compared it to a harmonic. Harmonics diverge, right? Then if I can show that my B sub n's, right, are always small, or I should say it the other way, my A sub n's, these guys are always bigger than these guys. If this one blows up to infinity and these are always bigger, then that one's got to blow up also. That's what this is saying. Does that kind of make sense? Is that a little clearer? Okay. So this is a this is a test, all right, and it's kind of funny because last class I did this lecture in my class yesterday, but my SD card ran out of room, so I only got the first 10 minutes of the lecture. So I told them I was going to do this lecture today and post it for them so they can have it, right? So we were talking about these tests, and there was some confusion while we were doing it, and we came up with a good analogy. I think it's a good analogy. I want you to look at this comparison test as like a pregnancy test, okay? All right, so here's the idea, is that let's say that we have a series, we don't know what it does. We compare it to a series, so let's say we say that this one is geometric and it converges, let's say, right? So we say, okay, we're going to compare it. Now you have to show this, right? Now what if you can't show this? What if this turns out to be not true? Does that mean that it diverges? See what I'm saying? Because if this one converges and we can show this, then that means that that one converges. But what if we can't show this? Does it mean that that one diverges? The answer is no. And the pregnancy test idea is this. If we do this and we can't show that, it's like a defective test. It doesn't mean you're pregnant or not pregnant. It's just that you don't know. The test failed. Does that make sense? Okay. So you gotta go buy a new pregnancy test and try maybe a different comparison. All right? I hope maybe as we do one, you'll see. It's strange? Yeah, I couldn't think of any other analogies. What's that? Yeah, I think so. Lasagna and... Okay, here we go. Let's do our first example. Okay, so unless I tell you otherwise, the goal here is to try and determine whether or not the series I put up here converges or diverges. Is pregnant, yes. So is this series pregnant?
That's how you're going to show your daughter the birth of the beast.
Mm-hmm. Yes.
If his morals don't converge.
All right. So what do we start with? Well, yes, if we're going to do comparison, right? But in the big picture of things, we start by running the nth term test first. So I would, I'm going to save us time. I'd write down nth term test, right? I take the limit as n goes to infinity of this, right? And that would go to 0, and that means that test would fail. So that's almost like a pregnancy test that failed already, right? It failed. It doesn't mean we're pregnant or not. It just means the test was defective, all right? So now we run through, is it geometric? So n is not in an exponent, so it's not geometric, right? What else? Harmonic? No, because that's not a constant over linear. And what about telescopic or collapsing? It's the same. They're the same thing, right? I would have to be able to factor this to be able to do partial fractions on that. Maybe I can't. I don't want to try it. Okay, I don't want to try it. All I want to do now is maybe run to the next test and see if I can use it. So when we look at this thing, it comes down to what in the world do we compare that to if we're going to compare it to something. So let me write down, first of all, what a sub n is in the problem. A sub n is the sequence that we're adding up, right? For b sub n? Let's see. Let me go through this first one, and then we'll this is what we need to figure out, right? So I would like for you to just take a look at this expression over here and think about if n is very, 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 very big, all right? If n gets huge, does this plus 3 really matter? Like adding 3 on the bottom of this really does not matter, right? If n is large enough. In fact, if n is really large, this doesn't even matter. The dominating term in the denominator is the 2n cubed, because n cubed overwhelms everything else because it's the highest power down there, right? So would you agree that that's, for big enough n's, that's approximately 4 over 2n cubed, right? For big enough n's, those are pretty close to one another. Would you all agree with that? If you let n go to infinity, this goes to 0 and that goes to 0. Right? They both go to 0 as you go out. Now, why would I pick that? Why would I not have picked, why would I have not picked plus the 4n squared there? Because that would also be a comparison, right? Like that? Like that would also work because I'm just taking out the plus 3. Why am I not going to use that and use that instead? It's easier, but remember what I wrote in red there a second ago? What did I write? You must know what it does, right? I have to know what this does in a series. So first of all, let me clean this up. Isn't this 2 over n cubed? Yes? And written in a series, 2 over n cubed, what type of series is that? It's a p series. Okay, that's what we ended class with last time. Remember this from last class. 1 over n to the p, right? 1 over n to the p. This will converge, and this is actually on your sheet, right? It's right under geometric series. This converges if p is bigger than 1, right? Now, does the 2 have any play in this? No, the 2 could come out of the sum if we wanted to. So this is really like 2 times 1 over n cubed. So this is a p series. P here is 3. That's bigger than 1, and therefore this converges. Okay? So I have the series I'm interested in. I've taken a look at the sequence. I've found a sequence that I think this one kind of compares to, and I know that that's a convergent sequence series that I'm comparing it to. So what must I show now? I want to show, WTS, I want to show what?
A sub n is less than b.
A sub n is less than b sub n. Why? Because this one converges. So if I can show that these guys are always a little bit bigger than these guys, then if these add up to be a number, that's going to have to add up to be a number. So now on your sheet here, under comparison test, do you see it down there under integral test? It says this. We're actually looking at, right in the middle. at? Oh, it's right there. So this is a comparison. Do you see this? If B sub n converges, that's what we have, right? And A sub n is less than or equal to B sub n for every n, then A sub n converges. All right? So this tells you right there what you have to show. Okay? So that's what I need to show now. I'm not done in any sense. All right, so now I go about, I want to show that A sub n is less than or equal to B sub n. So I write down A sub n. And I'm asking myself, really, this is a question, right? This is not a true statement. This is what I'm asking myself. Is that true, right? Is this a true statement that A sub n is less than B sub n? So when you put B sub n in here, you can put this here, or this down there, or you can put this down there. It's really kind of up to you. I'll put the simplified version, 2 over n cubed. Now, to figure out if this is true, let's just like cross multiply, okay? And when we do that, what do we get here? If I go here to here, 4n cubed, less than or equal, see, this is still a question mark, I don't know. And then 2 times all of this, right? Which makes that 4n cubed plus 8n squared plus 6. Y'all agree? And now, I see that these are the same, aren't they? So let's subtract that from both sides. So if I subtract 4n cubed from both sides, it goes away. And I get that statement right there. Now, do you agree that that statement is true? For n greater than, right? And remember, n here for us is 1, 2, 3, right? Now, it's important that we understand that n is greater than 0, and that it has been, because when I did this cross multiply here, I have an inequality. And if you multiply inequalities by negative numbers, it flips over. So I really had to be sure about n being 1, 2, 3, 4 earlier in the problem. But yes, at the end here, we can conclude that this is true. So as soon as you get to a point where you are happy that that's true, and you have to convince me also, like that would convince me that it's true. You can't just write this down and be like, yeah, check. No, you have to show algebraically that it comes out, all right? So we had a series, we compared it to something that we knew what it did, and then because it converged, we had to show that this inequality would hold. We've shown that it holds, and therefore we're done. So what we can say is, therefore, that series 4 over 2n cubed plus 4n squared plus 3 converges by the comparison test. So when I started this, right, I told you we would have done like nth term test first, and then we would have said it failed, and then we would have done, I would have written down, like when you're doing your work, what I'm getting at is when you're doing your work during the final, you need to be showing me what you're doing, okay? You can't just start doing random crap without telling me what test you're using, because we have all these tests. So I'm not going to be able to look at it and know right away what you're doing, right? So you want logical explanations on what you're doing. All right, next problem.
We wanted to find out what it converges to. Do we ever learn how?
Okay, so the question is, can we find out what it converges to? In general, it's pretty difficult to figure out what a series converges to in general. But with the aid of computers, you can get a pretty good idea. But just if you get an arbitrary series out there, to figure out what it adds up to be in general is very difficult. It's almost like, that's almost asking like, if you just hand me a random function, can you integrate it? Same thing, like chances are no, unless it was tailor-made for you to like have substitution work or integration by parts. Otherwise, we rely on other methods. Is that okay? Yeah. Did I tell y'all about the extra lecture I might do at the end of the semester during finals week? No? Okay. I might be offering an extra lecture. It would be optional, and it would definitely only be, I couldn't offer bonus points for it because some people can't be there, so it's not fair. I still don't know if I'm going to do it yet, but it's a lecture that I do on Fourier Series, which are a certain type of series. Oops, that's supposed to be natural log. anyway, it's like an hour and a half little lecture, and it takes us an hour and a half to figure out what a certain series adds up to be. It's one problem.
Is that related to like Fourier transforms?
Uh-huh. In some sense, yeah. Yeah.
So that's natural.
When would it be?
That's natural log of n.
When would it be?
I don't know yet. I don't know. I'm probably going to offer some time slots and see when the most people that would want to go would go. Okay, and I think I'm going to record it because I've done it in the past, but I've never recorded it. So I think I'm going to record it this time. So that way I can not have to do it again. All right, here we go. All right, so what would you do first here? Nth term test, right? So let's actually go through this. If I did the nth term test, I'm going to be doing the limit as n goes to infinity of natural log n over n. Now when I take that limit, I get an infinity over infinity, right? Now, can I convert those into that thing into a function of x? Yeah, natural log x over x, and then I could do L'Hopital's rule. So if I did that, what would I get? If I did L'Hopital on that. So is it okay if we start doing this? I know, like, we're violating many principles here. To say I'm doing L'Hopital's rule on a sequence is bad. But the understanding is that we would convert it to a function of x and then come back, right? Okay. So as long as we understand that, I think it's safe for us to just use that notation, all right? That would be the derivative. And now let n go to infinity, and what do you get? 0. And so this test failed, right? This test failed. All right, so now we think, is it geometric? No. Harmonic? No, nope. And telescopic or geometric? Telescopic or collapsing? No. P series? No. So all we're left with is comparison. So I'm going to do comparison test now. And what would you like to compare it to? So a sub n here is natural log n over n, and b sub n here is up to you. This problem's a little different than the last one. Because in the last one, we could just kind of look at if n got big, what was it approximately equal to, right? So I need someone to step up to the plate here and take a swing at this one. Bianca? Is Bianca here? No? That's you, right? You want your test? There you go.
Can you use like negative 1n? 1 over n?
1 over n?
Negative 1?
Not negative 1 over n. Yeah, I mean, I was going to wait till later to tell you all this, but I guess I'll say it now. Notice that every series that we've done has always been a positive series. In other words, we've always had positive terms here. Okay, that's been intentional. Yeah. Yeah, we're going to deal with it, though. We're going to deal with it in 8.4. All right, we'll deal with negative. Okay, so, but you said 1 over n, right? I mean, that's taking a shot at it, right? So if we look at this as a series, what type of series is that? Harmonic. So you're going to compare it to something that's harmonic. Now, I'm not telling you this is going to work. Okay, you suggested 1 over n. I'm going through it, okay? So harmonic, and it diverges. Okay, since this diverges, what must I show? I want to show what? A sub n is bigger than or equal to b sub n. So again, the idea here is that if these add up to become infinite, and I can show that these are bigger, then that one's going to have to be infinite also, right? So let's see if that works. Is natural log of n over n greater than or equal to 1 over n? All right, let's play that same game. Let's just multiply both sides by n. Can we do that? Multiply both sides by n. So you get natural log of n is greater than or equal to 1. Is that true? What does natural log look like? If we were to graph the function, right? This would be natural log of x. But natural log of n, where would we start?
1.
We start with n being 1, and what's natural log of 1? 0. So the sequence, right? Natural log of n starts here, and then it does this, right? Because it lives on that graph. So, and then we're asking, is it greater than 1? 1 is somewhere out here, right? Is natural log of n greater than 1? No, right? And this is the one problem I have with your formula sheet. Because on your formula sheet, I don't like the wording in this because it's not technically correct. Do you see there, where in the comparison test says, if b sub n diverges and a sub n is bigger than b sub n for every n. You see that? That's actually technically not correct. Because you don't need it to be, you don't need the inequality to hold forever. You need it to hold eventually. All right? So in the wording of those things in there, I don't mind if you change that where it says for all n to eventually. So this inequality is not true right off the bat, right? Like if I say n is 1, then obviously this is going to be 0, and 0 is not bigger than 1, right? Now, what's natural log of 1? I'm sorry, we already did 1. Sorry, natural log of 2. What is it? 0.69, so it's still not working, right? What's natural log of 3? There we go. So it takes till we get to 3, right?
Right.
But then after that, we're good. So this inequality is not true all the time, but this is true eventually. And once you get past a certain point, right, and for us it was 3, once you get to 3, here's 1, here's 2, here's 3. I actually drew it right. I wasn't planning on that. Okay, so once we get to 3 and on, it's going to be true, isn't it? So that's what I mean by eventually. Maybe it doesn't work for the first 2, maybe it doesn't work for the first 100. But if at some point on it works, you're good. All right? As long as it holds, though. See, like the graph shows me it's never going to come back down. It's never going to come back below 1. All right? So have we done everything we needed to do? Yeah? Therefore, what? Therefore, yep, this thing diverges, right? It diverges.
So that's only true for the second, like in the thing.
No, it's for the first one also. Yep. Are you talking about on the formula sheet?
Yeah.
Yeah, let's just take a look at this. I'll erase this here. So do you see where it says for every n here? That for every n can be changed to eventually. And that for every n can be changed to eventually. And I believe there might be more on here. Let me see. Let me get to the other tests. Alternating series. Yeah, for this one also. This one for every k can be, eventually. But we'll get to that one. Okay? All right, let's do another one. Yes.
Is that what, like, you eventually change for whenever it's converging as well?
Yes, that's what we were saying. Are you saying on here?
Yeah, because we did for when it diverges. But when
Yes, it works for converges as well. So on here, it works there and there, both of
Okay.
those.
Oh.
Yep.
But it only works if it's continuous, right? Like if it's, like, if that eventually, please, like, for whatever reason, that natural log were to dip.
Yeah, then we wouldn't be able to say that. We were using the fact that we know the shape of the natural log function, So now we don't have to show that. We just have to, it's our knowledge of the natural log function which allows us to say eventually. Okay. All right. The first thing we'd want to do here is the Nth term test, right?
Right.
Now, we finally have reached a problem where I actually I'm not interested in running L'Hopital on that. Just because the derivative of that looks pretty bad, right?
Yeah.
And we've seen with L'Hopital that sometimes L'Hopital can make things worse as you start applying it. So the Nth term test is there as a quick tool to rule out some things. Like, you know, if you take the limit and you get something other than 0, you're done. But in this one, I think I'm going to be taking more time trying to show that this limit goes to 0. So what I'm going to do is skip the Nth term test. I'm just not going to do it. And I'm going to run straight to a comparison. And that's because I've already ruled out that this is not geometric, right? It's not telescopic. It's not a P-series. It's not harmonic. So I'm going to do a comparison. My A sub n is just a nasty looking thing here. Now, we have to come up with B sub n. Treat this one kind of like we did with the first one that we did.
So if you did this one with just like the same numerator n plus 5, but denominator would be the 5th root of n squared.
Okay, I agree with this part, 5th root of n squared. I agree with that because when n gets really big, this dominates these two, right?
Okay.
And so we have like 5th root of n. But up here, we have n up there, right? And plus 5. The plus 5 doesn't matter in the big picture. So just n. And the reason I don't want plus 5 there is because then I'll have, I won't know what it does. Like with this, I'm going to be able to figure out what it does. I think, right? This is n to the first power over n to what power? 5 halves? No, 2/5. What am I? Whoa. 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 2/5. All right, that's what that means. And then, you know, we're just using properties of exponents here, like x to the n over x, x to the m is x to the n minus m, like that. So we're just going to subtract the exponents. So this would be n to the, what's 1 minus 2/5? 3/5? Right? That's what it is. Do we agree with this? So what now? Okay, can we move it to the bottom? Yes, we can move it as 1 over n to the negative 3/5, right? And that would be a p-series, with p being less than 1. So this would diverge, right? Now, you could also have just looked at that right there and just thought about what would happen. If that was your series and you start plugging in 1, then 2, then 3, and start adding them up, that's going to blow up, right? Wouldn't it? But we got it to here. So now, let's not confuse the sequence from the series. That means the series is 1 over n to the negative 3/5, which is p series, with p being negative 3/5, which is less than 1, so this diverges. Okay? If that diverges, then what is it that I need to show? A sub n is greater than or equal to b sub n. Now, I haven't talked about this but I want to kind of make sure you understand why is this inequality not something we look at? I mean, what if we were to show that A sub n is less than B sub n? What if that's what we were able to show? This diverges, mean it goes to infinity, right? And we're saying that all of these guys are smaller than all of the guys we compared them to. That means when we add these up, that sum is smaller than or equal to infinity, right? Which means it could be infinite, but it could be anything less than infinity. So that means it could converge still, right? Like 10 is less than infinity. Does that make sense?
Yeah.
Like this is like, oh, look, I'm going to show that this guy is smaller than infinity. All right, well, that means that could still be infinity. Or it could be a number. It could be anything. So it doesn't narrow it down. But if I flip it the other way, and I say this guy has to be bigger than this, then when you add them up, that's got to be bigger than infinity, and the only way it can do that is if it's infinity. Because infinity is not a number, right? So it's an idea that it just gets huge. All right, so that's what we need to show. All right, so can we show this? Can we show that n plus 5 over the fifth root of n squared plus 2n plus 1, can we show that that is less than or equal to, and you can use any of these. I'm going to use this one, and you'll see why here in a second. N over the fifth root of n squared. Let's see if we can show that that's true. Well,
Wait, I thought we're doing whether it's greater.
oh, did I flip that over? Oops, I just wrote it down wrong. I'm sorry. We're trying to show that. I apologize.
I was like,
Yeah, thank you.
Good kid.
Okay, I'm trying to show that that's true.
okay, so cross multiply this side.
Try cross multiplying. Right? It's starting to look pretty nasty. Okay, if I cross multiply and get this, right, and then times n plus 5, and then greater than or equal to n times, like that, right? Any ideas here? You could raise both sides to the fifth power. That's fine. Y'all want to do that? Okay. If I raise that, so this is multiplication, right? So if I raise this whole side to the fifth power, that goes to the fifth power, and that goes to the fifth power. So I'm going to, hey, let's not throw it away yet. Hold on. That's to the fifth power, greater than or equal to. Now, I n out in front, right? So that'll go n to the fifth power times this to the fifth power, which is just n squared plus 2n plus 1. So that's not too bad, right? Like I could just pass this through, right? N to the fifth through here.
If you divide by an n squared, though, you just
Oh, you could divide by n squared too. No, we'll do that now. That's fine. Divide by n squared, that makes it n cubed.
Right.
Agreed? So then I could pass this through. Let's do it. We have n plus 5 to the fifth power is greater than or equal to n to the fifth plus 2n to the fourth plus n cubed. All right, is that true? You sure? I'm not convinced. So how could you would have to expand out n plus 5 to the fifth power, right? N plus 5 times n plus 5 times n plus 5. Could we do that? Yeah, didn't we do this? Didn't we do this in here?
Yeah, no.
Okay, but do you really want to do that? Okay, so let's leave this as an open question right now, okay? It appears we've got the setup going, but our showing of the inequality seems to be a bit more challenging than anything we've seen so far, right? Okay. Then we're going to put this on pause. We're going to do another problem now, and we're going to run into a similar issue. And we're going to put that one on pause, and I'm going to give you one more, and we're going to run into a similar issue. And we're going to realize that the comparison test is great, but it's not the end-all, be-all, okay? So we need more than this test. So let me give you another one, all right? We are pausing on this one.
If we did Pascal triangle and solving inequality, would it work?
I don't remember, actually. I'm not sure if the test would fail or not. We'll leave that as an open question. So how about this one? How about n squared over 3n cubed plus 1? All right, so if we were to run through our little Rolodex of things, nth term test, L'Hopital's rule, we would get 0, the test would fail. It's not geometric. It's not telescopic. It's not harmonic. And well, you know what? We haven't mentioned this, but we could use the integral test here, because I could integrate that. If I let u be the bottom and du would be the top, we'd be off by a sign. We could do integral test. That's what we did last class. But we saw how tedious the integral test can be. So maybe I can do a comparison. So let's go with comparison. Comparison test. A sub n is n squared over 3n cubed plus 1. And b sub n, well, what do you think? If n is big enough, that plus 1 doesn't matter, right?
Right.
So this is really like,
Would you keep the 3?
yeah, you can keep the 3 there. Because, well, the reason why I don't mind keeping the 3 there is because this really comes out to be 1 over 3n, right? And that 3 doesn't matter, it's harmonic, right? That's a harmonic series? Okay, so this is harmonic. And it diverges. Okay, so what does that mean? Well, I need to show that if this one's going to blow up, right, I need to make sure that this one stays bigger than it. Yes?
I'm sorry, did you use L'Hopital's?
Nope.
Wait, how'd you get?
I just simplified it. I just canceled out 2 factors of n.
Oh, well,
Yeah.
that's tricky, man.
Yeah. Okay, so I want to show that a sub n is bigger than or equal to b sub n, right?
Right.
Okay, so let's do this. I need n squared over 3n cubed plus 1 to be bigger than or equal to 1 over 3n. I'll use this one. Cross multiply. You get 3n cubed is bigger than or equal to 3n cubed plus 1. Do you all agree? And subtract 3n cubed on both sides, and you get 0 is bigger than or equal to 1. Not today, right? That's not true. Any questions on this right now? What I'm doing? Why I compared it to this? No? How? What does this mean?
Test failed.
The test failed. This is a bad pregnancy test, okay? That's what I'm talking about. This does not mean that that converges. Okay, that's the issue that students run to. Say, oh, I'm going to compare it to a harmonic series that diverges, and when I try and do this, I come up with something that's not true. Well, that means that it converges. No, that means the test fails. I have a question here. I want you to look at this. Now pay attention closely to this, all right? Because this is not natural, what I'm about to do, until I do it, and then you'll see. Right here with this inequality, the reason why I had a problem was because when I subtracted 3n cubed on both sides, I got 0 over here, right? What if that had been a 4n cubed? What would have happened? When I subtracted 3n cubed on both sides, I would have got what over here? n cubed, right? Do you agree with that?
Right.
So could I have made that a 4? Now where did this come from? Where did this piece come from?
1 over 3.
This right here, right? When I multiplied there, it came from that 3 right there. Can I change that to a 4? Well, I made up this series myself, didn't I? This was my choice. Wasn't it?
Right.
So if I change this to a 4, even though that's not 4 over there, and change this to a 4, then this would become a 4, and this would become a 4, and now this inequality would now become n cubed bigger than or equal to 1, and that is true. Right? Why not? I get to come up with this myself, right? So how did I know to do that? I looked at this right here and I realized that the problem, the reason I was not able to hold this inequality true was because these were the same. Had this one been slightly bigger, then when I subtracted 3n cubed here and minus 3n cubed here, if that had been 4n cubed, then I would have been left with 1n cubed. And then it would have held. So I reverse engineered my comparison sequence, or sequence from that. Does that make sense?
So how much flexibility do we have? Could we have made it like 3n to the 4th
Where?
on the denominator? So that you come up, and you could have made it like a power series?
If you would have used 3n to the 4th here,
Yeah.
then you're going to have some issues here. There's a couple of things that would happen. If you make this 3n to the 4th, let me just do it. 1 over 3n to the 4th. You're now comparing it to a p series that converges, right? And therefore, this would become 1 over 3n to the 4th, but now your inequality you're trying to show is the other way around. And so when you cross multiply this like that and that, this one right here would be like a 3n to the 5th, less than or equal to, and then this side's going to be 3n cubes, and that's not going to be true. You see what I'm saying? So you can start tweaking this, but if you tweak it too much, then you can mess yourself up. So the whole point of this problem was to show you how the natural choice of our comparison didn't tell us anything. But by recognizing where we had an issue, we were able to go back and resolve it. Yeah? It's messy. That's kind of messy, right? Yes.
So the reason you changed it, well, I get why you changed it to 4, but I'm saying the reason you're allowed to do that is it because, like I know if you change it, like you said, if you change the power, it'll make it a p series, and that's completely different. But if you just change the constant, it's
Well, look, if I change that to a 4, then this is still 1 over 4n, right?
Yeah.
Which is still harmonic.
that's why.
That's right. That's right.
Okay.
And not only that, but I have control over my comparison, right? Like if this comparison didn't work, I could just try a different comparison. I have complete control over this sequence. I have complete control of it, over it.
As long as you don't change what it is. Like,
Well, if you change what it is, like if you change it to that, that's fine. Compare it to that. I have no problems with that, but make sure you use the correct inequality here, because that would flip.
Yes.
Yeah. It may or may not work. Okay, so that one worked. That one kind of didn't work, but then it worked because I got clever, right? Let's do this one. This will be the last one I do before I show you the new stuff. Can somebody look in their notes and tell me what was the example I gave you for telescopic? N squared minus 2n. And I started at where? 3?
N equals 3.
Okay, remember this? Remember that? Okay. So if on a test or some other place, I were to present this problem to you and say, does this converge or diverge? You would have to show it converges or diverges, and that's it, right? If I said find the sum, then that means you have to run through and do all the telescopic collapsing thing, right? So this problem we know converges. We did this in class. It's telescopic. I'd like us to try and use a comparison test to see if we can do it. All right? Let's see if we can. So comparison. So when we do the comparison test, a sub n is 1 over n squared minus 2n. And b sub n, just go with the same kind of logic that we've been using. What do you think we should use for our b sub n? 1 over n squared. Okay, that's p series, right? This series is p series. P is 2, and therefore it converges, right? Okay. All right, so what do I have to show if I'm comparing it to a convergent series? That a sub n is less than or equal to b sub n. All right, so now we go 1 over n squared minus 2n less than or equal to 1 over n squared. Now what? Cross multiply thingy, right? N squared less than or equal to n squared minus 2n, right? Am I going too fast, or is this okay? 0 is less than or equal to negative 2n. That doesn't work. That doesn't work because of what? I mean, n is always positive, right? So negative times positive is going to be negative, so negative is not going to be bigger than 0. So we can see here that that doesn't work, right? Our conclusion here is that the test failed and that's it. Unless we can tweak it. Can we tweak it? You want to do 2n on the bottom instead? Would that fix it? If I made this a 2, this a 2, would it still be a p-series convergent? Yes, right? That doesn't change anything. This inequality would stay the same. This would be 2. This would be 2. And now my new one would be what? N squared, right? Because I subtract 2 on both, or subtract n squared on both sides. I get n squared is less than negative 2n. What do you think about that? Still not true, right? Make what negative? Negative 2? So you're saying if I made that negative, then if we brought that over, it would be negative 3n squared. That might work, but do you see this is not coming out as clean as that last one? I mean, do you see that this is inherently different than the problem I just gave you? Okay. So I think I've shown you enough examples where things can get tricky to bring in the next test. All right? Yes?
What did you do with the 2 right there?
Okay, so I subtracted n squared here and subtracted n squared here because we're not working with that anymore. That goes away. 2n squared minus n squared is 1n squared.
Could you use 3n?
3n? Like 3 down here? Yeah, then that would have been 3n squared, and we subtract, we would have had 2n squared. The problem is that n squared is going to get bigger than n, right? Like you start plugging in numbers, and then not only that, this is a positive number, right? And this is a negative number, and your negative can't be bigger than your positive. That's the bigger issue, is that this is negative and that's positive. Make sense? All right, so we need a new test. Actually, on your formulas, it's not a new test. It's still in the comparison test. But here it is. This is actually called the limit comparison test. In our book, it's called the limit comparison test. And here's what it is. Basically, what it is this. Let's say you have, this is given, and you compare it to something you come up with. All right, so this is the same thing we've just been doing, right? But here's what the limit comparison says. Just take the limit as n goes to infinity of a sub n over b sub n. Okay, so it says take this sequence right here, divide it by this sequence, and take the limit as n goes to infinity, and hope to get a constant c, where that c is a positive number and not infinity. Okay. Now the notes don't say that. You can put that on here. That this limit has to be what the formula sheet says is that c has to be a positive real number. But basically that just means that this has to be a positive number and not infinity. Okay, now mechanically all we're going to do is take the ratio of the sequences within the series. We look at the sequence here, we take the ratio, take the limit, hope for a number. The conclusion is this. If this happens, right? If this happens, so I should put here, if this happens, then they both do the same thing. What the hell do I mean by that? What's that?
They both converge.
They either both converge or they both diverge. This limit being a constant tells you that they behave the same way. So if you were comparing it to something and you knew what that did, you knew that, let's say this was convergent, then you take this limit and get a constant, that's convergent. If this was divergent and you take this limit and get a constant, then that's divergent. Whatever one does, they both do, so long as this is true. Now, why? Why does that work? Okay, so let me try and explain this. I'll do my best. Let's say this is a sub n and b sub n, and we're going to take a look at their ratio. So a sub n is some sequence of numbers out here, right? And b sub n is some other sequence. Okay, I'm not even making them one be on top of the other. But what if, as I go out to infinity, the ratio of those terms is constant? What does that mean? So like, let's go out here. What if this red one is here? Let's say that the value of this right here is 4, and the value of this one is 2.
I mean, the distance between.
That means, yeah, so the a sub n is the blue one, right?
Yeah.
And this one, so that means if I take the blue and divide by the red,
Sure, it's the same.
if I'm getting a constant, then the ratio of this divided by this is constant. So this would what, be 4 over 2? So the ratio would be 2, wouldn't it? Now, what if we move out here, and now the blue one has come down. So let's say there, right? But we should be having a constant ratio. That means the red one would have to do what? Go down, right? So if I take that and divide it by that, that ratio would be 2 again. Make sense?
Yeah.
So what's happening is that if you can show that the ratio between the two sequences is constant, it means that as your b sub n starts to do something, the a sub n has to follow it within some ratio, right? So, but it's a fixed ratio. Does that kind of make sense? Like if this one goes up to 100, this one's going to go up to 50, according if we use the same ratio. If this one drops down to 2, this one's going to drop down to 1. So they stay together. Does that kind of make sense?
So they can't like flip.
Yeah, they can't flip over. They can't. One of them can't take off without the other one taking off with it, right? If this one converges, this one has to also converge to something. So this fixed ratio forces them to both do the same thing together. It's pretty awesome when you think about it in the big picture. But let's just see how awesome it's going to be for us here. Okay? Let's go back to this problem right here. You see this one? Let's do that one. We'll work backwards. We'll do this one first. I'm going to do the limit comparison. Okay, so when I do the limit comparison, a sub n is 1 over n squared minus 2n. And b sub n, let's stick with the same one, 1 over n squared. Right? That didn't work a second ago, did it? The pregnancy test